In today's video, I'm going to show you guys how to use Kirchhoff's loop rule. And we're going to start off with here really just a basic understanding of this rule and how it comes into play for different kinds of circuits, whether you have something that's very simple or you have a combination circuit that has multiple loops in it. So we're going to start off with a graph of electric potential versus position for a DC circuit. We'll describe how voltage drops across circuit elements like resistors in a qualitative way, so just kind of a more conceptual start, and then we'll learn how we actually write loop equations and choose loops within a circuit that we're going to use to then solve for unknowns in our circuit like potential difference, aka voltage, and also current. So let's go ahead and get into just kind of a basic little graph here for the electric potential versus position in this circuit. And so you see here we have a simple circuit. It's just a single loop, and we have some points that we're going to move across to graph how the electric potential changes as we move through this circuit. And so if we start at position A, we're going to start with this as like a reference point of 0 volts. And as we move across the battery in the direction of conventional current, which the direction of conventional current would be going in like a clockwise direction here. It would be going around this way because we have the longer line of our batteries on the left there that's telling us where our positive terminal is. So it goes from the positive terminal around toward the negative terminal. But with that direction of conventional current, if we start at point A and go to point B across the battery, we would see that as like an increase in voltage. So we treat going across the battery as a positive change in the electric potential. And in this case, with a 9-volt battery, we're starting at 0, and we would be going from point A to point B from 0 volts to 9 volts. So 0 to 9 to start. And then as we go from point B to point C across a wire, we'll make the assumption that our wire does not have any of its own resistance. So as we go from B to C, we have no voltage drop across just a wire, again, assuming that it is ideal and does not have its own resistance. As we go across our next resistor from C to D, we have a 100 ohm resistor there. We are going to have a voltage drop across that resistor of about 1.5 volts, bringing us down to 7.5 volts at point D. We'll talk a little bit more in a second here about how I came up with that number. But then from D to E, we're going across a wire again. So we have no change in the electric potential across our 0 resistance wire. As we go across our next resistor, a 200 ohm resistor, we're going to have a larger voltage drop of about 3 volts across this one. So we're going from 7.5 to 4.5. And again, we go across a wire from F to G. And now we have a drop across our 300 ohm resistor of 4.5 volts. So from G to H, we have a voltage drop. And H to I, we have a wire again. So if you're wondering here how we're coming up with this idea of a voltage drop, we can think of that in terms of energy, which I'm not really going to get too much into right now. But if we're thinking about what's going on with our circuit here, moving across a resistor, electrons moving through a resistor, there's a conversion from electric potential energy to thermal energy. So that drop in the electric potential energy correlates to a drop in voltage. So that's where we're getting this negative change in the electric potential. But then the way that we're coming up with an actual value for that electric potential change is simply Ohm's law. So we come up with that voltage drop by multiplying the current through that resistor times the resistance of that resistor. And to find our current, we would be using also that equation with the potential difference of our battery divided by the equivalent resistance of those 3 resistors that we have. So having done this math already with our battery voltage of 9 volts and an equivalent resistance of 600 ohms, our current through this circuit is about 0.015 amps. So I'm getting that first voltage drop here of 1.5 volts by multiplying that current, which is the same through each resistor, by 100 ohms. And then I can find the voltage across my 200 ohm resistor by multiplying 0.015 amps by 200 ohms. And then for the third voltage drop, so that's where we're getting here this voltage drop of 3 volts. And again, we have our 4.5 voltage drop. We're getting that from multiplying our current of 0.015 amps times 300 ohms. So we can see here where this connects to Kirchhoff's loop rule is that we're starting here before our battery with a voltage of 0, and we're coming back to a voltage of 0, or an electric potential difference, or an electric potential of 0, I should say, by the time that we've gone through this entire loop. And that's going to be true for any loop. So we can write this as an expression where the sum of the voltage in a loop is equal to 0. So if I trace any loop in a circuit and I combine all of the voltages across all of the elements in that loop, we can set that equal to 0. So that's kind of the premise that we're working with here for Kirchhoff's loop rule. So using the same circuit here, we're going to write out a loop equation that matches up with that graph that we saw on the previous slide. So if we start at point A and we travel around, we're basically going to ignore the sections where we just have wire, like so from B to C, D to E, F to G, and H to I, because we don't have resistance there. But wherever we have a resistor, we're going to have a voltage drop, and wherever we see a battery, we're going to have a voltage gain. So if I start at point A and I go across the battery, we're going to look at this as we have this positive battery voltage. I'm going to call this resistor 1. We'll write it in terms of variables first. This will be resistor 2, and this will be resistor 3. And then the current in this circuit I'm just going to refer to as I. So my battery voltage minus the voltage across resistor 1 minus the voltage across resistor 2 minus the voltage across resistor 3 is equal to 0. So that incorporates all of the elements that I cross over as I go through this loop around my circuit, starting at point A and creating this like closed loop around the circuit. So with this one here, we don't really need to use the loop rule in order to solve for something. So for example, if we were trying to solve for current, we could just find the equivalent resistance by adding our 3 resistors, those resistances together, and dividing the battery voltage by the total resistance. But what we're going to see here is that when we have a more complex circuit where your current through each resistor is not all the same, is really where this is useful, is for each of these terms in our loop rule, we'll rewrite this as current times that resistor's resistance. So we're going to be really careful here to label our currents and our resistors so that we can tell where if we have 2 different currents because we have junctions, we are labeling those differently. So let's get into our example problem here and work through this with a circuit that would actually require us to use the loop rule. So in this circuit, we have a few more resistors. We have a junction here. So a junction is a place where the circuit kind of splits off. And what our job is to determine the current through the 150 ohm and the 300 ohm resistors, which are in 2 different branches of this circuit. So if you, in a problem like this, so here's some problem solving tips for you. If you have this circuit given to you, you have the picture of it, you want to go ahead and start off by labeling your circuit with the currents and the resistors. So if you have just the numbers here, I always like to work with variables until I have my equation kind of simplified all the way down to where I'm solving for my unknown quantity. But here would be our battery. I'm going to call this resistor 1, resistor 2, resistor 3, resistor 4, and resistor 5. So I can label my resistors that way. And I also want to indicate here where I have my different currents. So I have my total current that is going to go from the battery to through R1 to this junction, but then that splits off. So I'm going to call that my total current I1. And then we have some amount of that current that splits off and goes through resistors 2 and 3. I'm going to label that one I2. And then I also have the current that goes up through this branch, and I'll label that one current 3. And then at this junction here, our current joins back together, and we have that same current I1 that goes back through the battery. All right, so, and again, it's really important to label these, because if you don't kind of separate out your labels for I1, I2, and I3, and you just label them all I, that's going to mess you up, because if you just label them I and you treat them as if they're all the same, that's not correct, because your total current I1 splits. Some of it goes across 2 and 3, some of it goes across 4 and 5, so we have to give those different labels. So in addition to that, if we think about here the loops that we have 3 different possible loops that we can make. We don't need all of them, but we have some options here. So we have a loop that goes around the outside of the whole circuit. We can take that outer loop. We also have a loop that goes around this bottom part here. A third option for a loop would go around this top section. And again, we won't need all of those, but we do need at least one of those to solve this problem. And the more complex your circuit is, probably the more loop equations you're going to need, because you'll have more unknowns and therefore need more equations. So let's work on writing a loop equation for that outer loop. So if we're going around our outer loop here, as we go through that, and again, we're going in the direction of conventional current. So if we're going in the direction of conventional current, as you go across the battery, as long as we're going from the negative terminal to the positive terminal, that's a positive voltage. And then as we go across any resistors, we think of that as a voltage drop. So those voltages are going to go into our equation as negative. So to start, I always like to start with the battery. You definitely don't have to, but for that outer loop, our battery voltage is positive. We would be subtracting the voltage across R1, subtracting for R4, and subtracting across R5, and we're setting our equation equal to 0. So the idea here again is that the sum of the voltages in the loop is equal to 0. So we know here that our battery voltage is 9 volts. We know the resistances of all our resistors, but we're going to find the current here. Our goal right now is to find the current through the 150 ohm resistor. And the current through R4 and R5 is the same because those two are in series with each other. So we're going to continue to break down this equation until we get a way to solve for that current, which we've labeled I3. So I can keep my battery voltage term, and I'm going to write the voltage across R1 as I1 R1. Okay, so that's just coming from Ohm's law. Delta V is equal to IR. And then we'll do that again where for resistor 4, the current going through resistor 4 is the one that we have labeled I3 times R4. And then we also have that same current I3 that goes through R5. And we're setting that equal to 0. Okay, so we have an equation here now that has just one unknown in it. We can simplify this and solve for I3. Or actually, you know what? Let me back up a quick second here, because we actually haven't solved for I1 yet. So if we, and I'm going to kind of assume here that you're okay with solving for the total current in the circuit. So recall here that our total current would be our battery voltage divided by the equivalent resistance for our circuit. In another video here, I show you how to resolve these more complex circuits. So if you're having a little bit of trouble with that still, if actually like getting the equivalent resistance for a circuit like this is something that you're struggling with, check out this other video that I have. This will help you. I go through a few examples of how to do that, but I'm not going to go through all the steps here. So our total resistance for this particular circuit is 267 ohms. Our voltage is 9 volts. So our total current is 0.034 amps. So we'll take this I1 to be known, so that's our 0.034, and I3 is our unknown. So if we solve this for I3, our equation looks like this. We have our battery voltage minus current 1, resistance 1, divided by R4 plus R5. So let's go ahead and plug those numbers in and see what we come up with for an answer. So 9 volts, 0.034 amps times 100 ohms, and 100 ohms plus 150 ohms. So that gives us a current through that resistor that is equal to about 0.022 amps. So that is the current that goes through this section of our circuit. So it's that 0.034 amps is in this branch down here. The 0.022 amps goes through R4 and R5, so we've solved for the part of our question where we're finding the current through the 150 ohm resistor. And then we don't actually have to do a loop equation to find I2. So if you're familiar with Kirchhoff's junction rule, the junction rule tells us that the current into a junction is equal to the current that comes out of the junction. In other words, I1 is equal to I2 plus I3. So the simplest way to solve for I2, which is the one that goes through R2 and R3, which is our 300 ohm resistor, we would subtract that current that we just found from the total current to get about 0.012 amps. All right, so we could also use a loop rule. It would be just a little bit of a longer way to do that. But let's take a look here. Like if you were to write a loop rule equation for the loop here, for this little like inside guy, which would contain that branch that I2 goes through, we could write that as our battery voltage minus I1 R1 minus I2 R2 minus I2 R3, and setting that equal to 0, we would be able to solve exactly like we did for I3, we would be able to solve for I2. And we would get the same answer. All right, so if you're also not very familiar with the junction rule that I just mentioned, where we did this down here, I also have a video on that that can help you out. It's a very simple rule, but definitely very helpful, especially if you have a more complex circuit. It's something that can help you find current through certain branches in your circuit. So check out that video as well. And I also have another one here for you guys that will help you with just walk through more examples of using the loop rule with the kind of increasingly more complex circuits. So I hope this helped you out. This is Kirchhoff's loop rule, just the basics. So check out some of my other videos and make sure that you subscribe here because I'm coming out with videos every week. Just on all things that are going to help you out with your physics class, especially your AP Physics 1 courses right now, and also AP Physics 2 videos more of those are coming soon. All right, guys, see you next time.